So let's talk about energy now, as I told you. And let's first introduce some basic thermodynamic concepts. What is a thermodynamic system? Well, for our purposes, it's our body, it's our continuum medium, okay? Which is made of particles, okay? And every particle has some properties. So all these particles, those properties that are of our interest for thermodynamic purposes are called the thermodynamic variables. So in that context, we call that mu1, mu2, mu_n. And there are n, for every particle, there are n properties that are of our interest. Okay, they are called thermodynamic variables. Okay, the thermodynamic system in principle are considered isolated if it cannot change anything with the surroundings. So, an isolated system is a thermodynamic system, a body, that is isolated. As the word says, there is no possibility to change anything with the rest. For instance, imagine a completely, thermal isolated box, which is also prevent with no windows. So theoretically, if that isolating box was perfectly isolating, then there wouldn't be any way to exchange neither mass nor heat, nor to make external forces. Imagine that we isolate them in the space, so there is no gravity, so there is no way of introducing actions from this system from the exterior. In fact, there is no perfect isolated thermodynamic system in the world, because anyway, if the isolation is the best we can imagine, there is always some possibility of changing mass through particles that go, some atomic particles or whatever. So the only system then that cannot change anything with its exterior is which one? The one that has no exterior. The universe. So the universe, which is a system that by definition has no exterior, is the only perfectly isolated system. The other isolated systems are in fact pseudo-isolated systems. But anyway, we consider that we can produce some good isolated systems, and then we will call these systems isolated. And then open systems are the others, those that can change matter and heat with the surroundings, okay? And then another concept is that, imagine that if we are considering any thermodynamic variables in our system, we could imagine a space of n dimensions. Of course, if dimensions are more than 3, we cannot imagine, but we can make the abstraction. And let's consider that we have only two thermodynamic variables. Then we can consider a space in which in ordinates we set one thermodynamic variable, and in abscisses we have another thermodynamic variable, okay? And then at any time of the process, we can imagine that these thermodynamic variables take a certain value, so they can be represented by a certain point in this space, okay? And every point of this can be then considered a thermodynamic state. So a thermodynamic state is a point in the thermodynamic space, and it's characterized by a certain value of the thermodynamic variables. Nothing else, many words to say something that it's almost trivial. So we have n variables, we can produce in a space, every of these variables now is called thermodynamic variables, and that's called the thermodynamic space, and all the points are called high thermodynamic states. Okay. Then another concept, thermodynamic process. Of course, the system, our body, doesn't keep in general constant the thermodynamic variables. So these thermodynamic variables vary a long time, and then in the thermodynamic space they produce a certain path that we imagine continuous. So at the beginning of the process that we are imagining, there was a value mu1a, mu2a that defined a certain state in our processor, and then there is a variation of that until the end of our process of interest at point B, characterized by values mu1b, mu2b. And this path is called a thermodynamic process. Could happen that the end of the thermodynamic process, following this way, ends at the same point, so for the same values, than the original variables. Then this thermodynamic process is called closed cycle. A closed cycle then is a thermodynamic process where the end coincides with the beginning. Okay, that's it. Okay. So that's very easy. It's a little more complicated to define what is a state function. Mathematically, it's very easy. State function is a function that is defined in a unique way by the values of the thermodynamic variables. So it's a function of the thermodynamic variables that returns a unique value, whatever is for a given value of the thermodynamic variables. Okay? So mathematically, we'd say that this is a univoc function. Okay? So or a univoc mapping. For every value at the original space, we return just one value at the final space, at the image space. But maybe, what happens, why is that of interest in thermodynamics? Because in thermodynamics, many times, that function that we consider uniquely valued, instead of giving the function, many times, it's much easier to define the function not by the mapping itself, but in terms of the increments. For instance, it's easy to say, okay, imagine that we have two thermodynamic variables. Every increment of this function is produced by an increment differential of mu1 of the first thermodynamic variable and an increment differential of mu2 of the second thermodynamic variables. And then we say, well, the variation of phi when this increment of the thermodynamic variables is given by a certain function, mu1, mu2, times the mu1, plus a certain function, f2 of mu1, mu2, times differential mu2. So many times, the functions are described in that incremental way, rather in this closed form way. Okay? And then, we could wonder, okay, if I define a function by one way like that, I am defining uniquely the result or not. That's the point. So if through that I'm defining something that is unique, then what I'm defining phi can be considered a state function. Otherwise, it's not. So this is an example. Imagine that I have a function phi, and I define the variation of phi as a certain f1 of d mu1 times f2 times d mu2. So imagine that I start my process at point A. Okay? At point A, where the function has a certain value, phi a, that value here. Okay? And then imagine that I define two thermodynamic processes ending at the same point, at point B. But one thermodynamic process is that incrementing d mu2 directly from A to point B, but another thermodynamic process that goes to A, back to here, and then goes back to B. They both start at the same point and end at the same point. But what is the result that I would obtain if I replaced all this space and obtained the value of B of the function as the value of A plus the sum of the all increments produced in the way? So if the way is gamma 1, that one, the process will be starting here, I add increments, and I go this way to B. And the final value that I obtain by following the path, the thermodynamic process gamma 1, would be, starting from here, I will obtain here. But let's now imagine that I just look for the point B by producing, considering a thermodynamic process which starts at the same point A and ends at the same point B, but being different, gamma 2 different from gamma 1. For instance, that one. Moving back, when I move back from that point, I'm moving that way. And then when I go right to that point, I'm moving that way here. So the value of phi that I have obtained is different through path gamma 2, is different from the value of phi that I have obtained when I move through process gamma 1. So why is that? Because that function phi is not unique. You know, for every mu1, mu2, I don't have just one phi. I have two, that and that. Okay, it's a convex such that if it was open, like just a plane or whatever, for every phi 1, phi 2, I would obtain just one value phi, and then whatever was the path, the final value ending in a process that starts at a certain point and ends at a certain point of the thermodynamical space, then the final values of phi, by incrementing that to the process, would be the same. But if it's not, then what happens? Then the final result depends on the path. If path is gamma 1, I obtain final result B. If pi is gamma 2, that one, then the result is that point with a different value of phi. What does that mean? That this function phi, defined in that way, is not an state function. And a state function is then that thermodynamic function or mapping of the thermodynamic variables, but returning uniquely a unique value of phi for any values of the thermodynamic variables. Or, in other words, that in an incremental process, through the same 2 points, A and B, in the thermodynamic space mu1, mu2, for the same ending and endpoints, the result is independent of the way, of the path. If it's dependent on the path, then means that the function is not an state function. Okay? So an state function, the goal of the state function is to define something that characterizes just by providing the values of the thermodynamic variables, then the function is characterized with no doubt. But if the function is characterized depending on what is the path that I have to follow to arrive to it, then this doesn't define the state. So it's not a state function. Okay? That's the concept. So I hope that with that, more or less, you have the idea that in general, when we aim at describing physically our properties, we look, and stating theorems and principles, we look for state functions. Defining that a certain property is a state function, we are defining something. We say that this property defines the physics in a unique way, which is not trivial. Okay? We will find reasons for that. Look, let's now consider the power and the first law of thermodynamics. So we have there are two ways of introducing power per unit of time, so work per unit of time, into the body. The mechanical power and the thermal power. Okay? And the sum of them, this is the mechanical power, this is the thermal power, is that. Look, what happens if we consider the mechanical power? We do experiments, and then we see that the mechanical power depends on the thermodynamic process. So if I start in a certain point, and I am in a certain point, and I arrive and I measure the thermodynamic power or the mechanical power at the beginning and at the end, the result could be different if I follow different paths. So what can we say? That this P is not an exact differential. P delta T is not an exact differential. Maybe I didn't mention something, maybe, sorry, let me just rewind a little bit. So when the way of characterizing a thermodynamic a function as a state function is that this is not an increment, it's a differential. It's a differential. And then the differential means that the value at phi and a, when this is an exact differential, that is independent on the path. And the way of making sure mathematically that this is an exact differential is just if this f1 and f2 fulfill some conditions, which is the cross derivative equality. So derivative of f1 with respect to mu2 is equal to derivative of f2 with respect to mu1. Okay, and so on. So if this is an exact differential, then I can integrate them in a unique way, in a function. If it's not, then I can work with that, but I cannot integrate that. Okay? And then, if I cannot integrate that, I cannot define in phi as a closed form, as a state function. So now, let me go back here. Let's consider the mechanical power, P, multiplied by dt, and consider if this is an exact differential. Well, it's not. How do I know that? Because I do experiments, and I just measure the P dt, the mechanical work, at the beginning and at the end for different paths, and I see that this is not the same. So P, the differential of T, is not a differential exact differential. Okay? In other words, P is not a state function. Okay. What about QE, the differential of T? So I just measure the thermal work in my system, and I just do a process, a thermodynamic process. I start with a certain point and finish with a certain point. And I do that in different paths. And the result of the value of the heat or the power in the medium is not the same. So that means that QE is not a state function. Okay? Or in other words, QE times the differential of T is not an exact differential. However, if I do experiments and I measure the sum of both, so I do experiments from one point A and one point B, and I measure not just the mechanical work and not just the thermal work, but the sum of both, so all the external work, then I find that disregard the path, the result is very similar. So I can, after these experiments, some people postulated the following. Okay, in a thermodynamic system, the mechanical power is not an exact, is a state function. The thermal power is not a state function. In other words, P over QE times differential of T, every summand is not an exact differential, but the sum it is. So they postulate that exists something, the total energy of the system, which is called epsilon, a scalar, which is defined as the variation of the external power plus the mechanical power plus the thermal power per unit of time. So this is a state function. We postulate that this is a state function. So differential of E is a differential, an exact differential. Okay? So the energy is unique for every point at the thermodynamic space. It's unique. So I can think of it as a state function, a property, which is unique. And that's the first part of the postulate. There exists some epsilon, which is a differential exact, so it can be integrated. It can be integrated from that. If I know this and that, then this epsilon provides a unique solution in terms of as a mathematical function. Okay? Then, that's not all. The second part of the first law of thermodynamics says the following. There exists another function, U, which is called not the total energy, but the internal energy of the system, which is postulated to be a function of a state. A function of a state. It's postulated also to be a function of a state. Okay? And, by the way, that is a property which is extensive. By the way, that's something new. When we talk about properties, we could say that there are properties that are called extensive and there are properties that are called intensive. What is an extensive property? Look, in words it's very easy. One property is extensive is we can assume that the contents of the property in the whole is the sum of the contents of the property in the parts. For instance, if I talk about the mass of imagine that every one of us is a particle in a continuum medium. If I talk about the mass or the volume of the class, is it the sum of the mass or the volume of every one of us? What do you think? Yes. So mass and volume is an extensive property. Okay? But let me now think of another property that you are very familiar with. For instance, temperature. So the temperature of the class is the sum of the temperatures of every one of us? No. So temperature is not an extensive property. Okay? So whenever a property is postulated to be an extensive, we are postulating that it can be defined the specific contents of this property. What is the specific contents of this property? The contents of this property per unit of mass. So that the contents of the properties in the whole is the sum of the specific contents, in that case U small, times the mass, which is the contents in one particle, summed by all the particles. In other words, that's something that you have to keep for the future. One property is extensive, we postulate it's extensive, immediately we can postulate that there is some density of this property or some specific contents of this property, and the whole contents of the property can be obtained by sum, that is by integration, of the specific contents U or the density of the property rho U in the contents. Otherwise, if that was temperature, temperature has no specific contents. We cannot talk of the density of temperature or the specific contents of temperatures, because it has no sense talking of temperature per unit of mass. Okay? Because the temperature of the whole mass is not the same, the sum of the temperatures for every particle. It's not an extensive property. Well, so just close this parenthesis. The second part of the first principle of thermodynamics postulates that there exists another state function, U, which is also postulated to be extensive. So immediately there exist the specific contents of these properties, small u. So the contents U of U in the domain B, so the capital U is equal to rho U differential of B. And then it also postulates the following. That variation of this internal energy summed to the variation of the kinetic energy per unit of time is equal to the variation of the total energy per unit of time. In other words, what is that saying? That internal energy is that part of the total energy which is not kinetic energy. Okay? So let's see what we have defined here. First, there exists some total energy of the system. So it's an energy, it's an exact differential, it's something which is univocally defined for every state. That is the sum of the external power plus mechanical power plus the external heat power, thermal power, per unit of time. That's first. Second, I define, or they define, that there exists another energy, which is a state function too, which is called the internal energy, which is extensive, and then that is that part of the total energy which is not kinetic energy. That's it, okay? So that's the postulate. That's the postulate. That's the postulate of the first law of thermodynamics.